Right now, more than 13 billion miles from Earth, a spacecraft the size of a small car is drifting through interstellar space at 34,000 miles per hour. It left home in 1977. It has no sun to warm it, no service crew, no replacement parts. The temperature of the space surrounding it is close to absolute zero. Every textbook says it should be a frozen relic by now. It is not. Voyager 2 is still alive, still transmitting, still warm enough to function, and the reason why is one of the most brutal engineering stories ever told. NASA has spent nearly half a century deciding which pieces of this spacecraft must die, so the rest can keep whispering back to Earth. This is how they did it. If you enjoy stories about the machines we sent to the edge of everything, consider hitting that like button and subscribing. It helps more than you think, and we have so much more ahead. Now, get yourself comfortable, let's begin. When Voyager 2 launched from Cape Canaveral on August 20th, 1977, strapped to the upper stage of a Titan Centaur rocket, it entered a thermal environment dominated by the Sun. At 1 astronomical unit, Earth's distance from the Sun, solar radiation delivers roughly 1,360 watts of energy per square meter. That is an enormous heat source. Spacecraft operating near Earth must actively manage solar heating, using reflective coatings and thermal louvers to prevent overheating. In this environment, staying cool is the problem. Staying warm is free. Voyager 2 spent less than 2 years in this comfortable zone. By July 1979, it had reached Jupiter, 5 times farther from the Sun than Earth. Solar intensity at Jupiter is only about 4% of what it is at Earth's orbit. The Sun still mattered, but it had become a dim presence rather than a dominant force. The spacecraft's thermal balance was already shifting toward internal heating as the primary source of warmth. Jupiter's own environment added a temporary complication. The giant planet's intense radiation belts bombarded the spacecraft with charged particles, generating secondary heat in the electronics. But this was a brief encounter, lasting days, not years. Voyager 2 flew past, collected its data, and continued outward. At Saturn, reached in August 1981, the Sun delivered barely 1% of the energy it provides at Earth's distance. By the time Voyager 2 arrived at Uranus in January 1986, it was 19 astronomical units from the Sun. Solar heating had become negligible. The spacecraft was now thermally sustained almost entirely by its own RTGs and internal electronics. This was not a crisis. The thermal design had anticipated deep space operations. The insulation blankets and internal heaters were doing exactly what they were built to do, but the RTGs had already been running for nearly 9 years, and their power output had dropped by roughly 35 watts from launch levels. Neptune, reached in August 1989, was 30 astronomical units from the Sun. The solar energy reaching the spacecraft at that distance was roughly 1/900th of what it receives at Earth. The Sun was still the brightest star in Voyager 2's sky, but it was no longer a heat source in any meaningful sense. It was a bright point of light, visually stunning but thermally irrelevant. The spacecraft had entered a regime where its survival depended entirely on internal power. Every watt of electricity consumed inside the bus was a watt of warmth. Every watt lost from the RTGs was a watt of warmth that would never return. After Neptune, the spacecraft had no more planetary targets. NASA extended the mission, renaming it the Voyager Interstellar mission. The goal shifted from planetary science to studying the outer heliosphere, the region where the Sun's magnetic field and solar wind interact with the interstellar medium. For the next 3 decades, Voyager 2 flew outward through increasingly empty space, crossing the termination shock in August 2007, where the solar wind slows from supersonic to subsonic speeds, and entering the heliosheath, the turbulent boundary region between the Sun's domain and the space between the stars. On November 5, 2018, Voyager 2 crossed the heliopause at a distance of approximately 119 astronomical units from the Sun. The heliopause is the boundary where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. Crossing it meant that Voyager 2 had left the Sun's protective bubble entirely. The plasma surrounding the spacecraft was no longer solar material, it was interstellar material, gas and dust and charged particles that had never been inside the heliosphere. The instruments confirmed the crossing in real time. The plasma science instrument detected a sharp increase in plasma density. The magnetometer measured a change in the magnetic field direction. The cosmic ray subsystem recorded an increase in galactic cosmic rays and a corresponding drop in particles originating from the Sun. For the first time, a spacecraft was directly sampling the environment between the stars. But from a thermal perspective, the heliopore's crossing changed almost nothing. The interstellar medium on the other side of the boundary is so thin that it provides no measurable heating or cooling. The temperature of Voyager 2's bus was determined, as it had been for decades, by the balance between internal electrical heating and radiative losses through the insulation. The crossing was scientifically historic but thermally irrelevant. What the crossing did confirm, however, was that Voyager 2 was now truly alone. There was no solar wind to buffer it, no magnetic bubble to shield it, no remnant of the Sun's influence to provide even a symbolic connection to the star it had orbited for 41 years. The spacecraft was embedded in a medium that stretches between the stars for light years in every direction, a medium so empty that individual atoms are separated by distances measured in centimeters, a medium where the concept of weather or climate or seasons has no meaning. This is the environment Voyager 2 occupies today, not the dramatic void of science fiction, filled with swirling nebulae and looming asteroids, a featureless particle-thin emptiness where nothing happens on timescales shorter than millennia. And in that emptiness, a machine the size of a compact car, wrapped in reflective blankets, heated by decaying plutonium, is still warm enough to function. That is approximately 13 billion miles. A signal sent from NASA's Deep Space Network travels at the speed of light and still takes more than 19 hours to reach it. If anything goes wrong, the earliest engineers on Earth can even learn about the problem is nearly a full day later. The earliest they can respond is a full day after that. There is no repair crew, there is no backup spacecraft, there is no second chance, and yet Voyager 2 is still alive. Not alive in the poetic sense, alive in the engineering sense. Its computers are processing commands, its transmitter is sending data, its magnetometer is measuring the magnetic field of interstellar space, its plasma wave instrument is listening to the faint electrical hum of the medium between the stars. These instruments require power. Power requires heat. Heat requires a source. And the source that Voyager 2 depends on has been slowly dying for almost 50 years. This is not a story about how cold space is. Everyone already knows space is cold. This is a story about why a machine that was designed to last 4 years is still functioning after nearly half a century in the most hostile environment human engineering has ever confronted. The answer is not magic. The answer is not luck. The answer is a brutally calculated series of sacrifices that began decades ago and continues to this day, with engineers on Earth carefully choosing which parts of the spacecraft must be allowed to die, so the rest can survive a little longer. To understand why Voyager 2 has not frozen, you first have to understand what keeps it warm, and that begins with a metal called plutonium. Each Voyager spacecraft carries 3 radioisotope thermoelectric generators mounted on a boom that extends away from the main body of the probe. These generators are not reactors. They do not sustain a chain reaction. They do not split atoms on command. They are, in the simplest terms, containers of radioactive material that produce heat as a byproduct of natural decay. The fuel inside them is plutonium-238, an isotope selected specifically because it decays by emitting alpha particles, which are heavy, slow, and easy to contain. When those alpha particles slam into the walls of the fuel capsule, their kinetic energy converts into thermal energy, heat, constant, steady, and completely automatic. At the time of launch, each of Voyager 2's 3 generators produced approximately 2,400 watts of thermal power. That is a combined total of roughly 7,200 watts of raw heat pouring out of the plutonium fuel. But here is the critical detail that most people miss. Only a small fraction of that thermal energy was converted into electricity. The generators use silicon-germanium thermocouples to exploit the temperature difference between the hot plutonium core and the cooler outer casing, producing electrical current through a principle called the Seebeck effect. The conversion efficiency was roughly 6.5%. That means each generator turned about 157 watts of thermal power into usable electricity, and the remaining 93% or so of the heat was radiated away into space through the generator's cooling fins. 3 generators, 157 watts each. That gave Voyager 2 approximately 470 watts of total electrical power at launch. That is less than the power consumed by a typical household kitchen blender. That is the entire energy budget for a spacecraft carrying 10 scientific instruments, a high-gain antenna, onboard computers, heaters, attitude control systems, and everything else needed to navigate the outer solar system and survive beyond it. 470 watts. That was the peak. The number has only gone down since. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half the remaining fuel decays into other elements and stops producing useful heat. The process is exponential. The fuel does not lose power in a straight line. It loses a fixed percentage each year, roughly 0.8% of its remaining output. In practical terms, Voyager 2's generators lose approximately 4 watts of electrical capacity every year. 4 watts may not sound like much, but when your entire power budget started at 470 watts and has been declining for almost 5 decades, 4 watts per year is relentless. It compounds, it accumulates, and it never reverses. By 2026, the generators are producing less than half of their original electrical output. The spacecraft now operates on something in the range of 220 watts. That is less than a single bright incandescent light bulb. And from that dwindling supply, every system on the spacecraft must be fed. The computers, the transmitter, the science instruments, the heaters that keep critical components from dropping below their minimum operating temperatures, the attitude control system that keeps the antenna pointed at Earth. Every one of these systems draws power, and every watt drawn is a watt that cannot go somewhere else. This is where the survival story begins to sharpen into something painful. Because power is not just electricity on Voyager 2, power is heat. The generators sit on a boom, separated from the main spacecraft body. Their waste heat radiates outward into space through metal fins and does not significantly warm the rest of the probe. The electricity they produce, however, flows through cables into the central electronics bus, the 10-sided aluminum structure at the heart of the spacecraft where the computers, instruments, and control systems live. When that electricity powers a heater, the heater converts it into thermal energy inside the bus. When it powers an instrument, the instrument's circuits generate heat as a byproduct of their operation. When it flows through the spacecraft's wiring and voltage regulators, even those components produce small amounts of waste heat. In every case, the electrical power delivered to the bus eventually becomes heat inside the bus. This heat is what keeps Voyager 2 alive. The spacecraft bus is wrapped in multi-layer insulation blankets, sheets of reflective material layered together to minimize the rate at which heat escapes through radiation. These blankets act like a thermos. They do not stop heat loss entirely, but they slow it dramatically, reflecting thermal radiation back inward and reducing the amount of energy the spacecraft needs to maintain survivable temperatures. The bus also uses thermal louvers, mechanical vents that can open or close to regulate how much heat is released. When the spacecraft was closer to the sun and generating more power, the louvers helped prevent overheating by venting excess warmth. Now, decades into the Interstellar mission, overheating is no longer a concern. The louvers are largely closed. Every fraction of a watt matters. The result is a thermal equation that governs Voyager 2's survival. On one side, heat is generated inside the bus by the electrical systems drawing power from the generators. On the other side, heat is lost through radiation, escaping through the insulation, through instrument apertures, through structural connections to booms and antennas. As long as the heat generated inside the bus exceeds the heat lost through radiation, the interior stays warm enough for electronics to function, for fuel to remain liquid, and for the mission to continue. But here is the problem. The heat generated inside the bus depends on how much electrical power is being consumed there, and the electrical power available has been falling by 4 watts every single year since 1977. Every year, there is less electricity flowing into the bus. Every year, less heat is produced. Every year, the interior of the spacecraft gets a little colder. For the first few decades, this cooling was manageable. Voyager 2 had margin. It had power to spare. It had heaters dedicated to keeping sensitive components warm, and those heaters could run without threatening the overall power budget. But as the generators weakened, those margins shrank. Engineers began making choices. Hard choices. Choices about what to keep and what to sacrifice. The heaters were among the first things to go, not all at once, but gradually, over years. A heater protecting a particular instrument would be turned off when the power it consumed was needed elsewhere. The instrument might continue working at a lower temperature for a while, or it might not. Either way, the heat it had been contributing to the bus interior disappeared along with its power draw. Every heater shutdown reduced the total thermal energy inside the spacecraft. Every shutdown brought the coldest components a little closer to their minimum survival temperatures, and there is one temperature limit that matters more than any other: the hydrazine freezing point. Voyager 2 uses hydrazine as its thruster fuel. Small rocket motors burn this chemical to produce the tiny adjustments in orientation that keep the spacecraft's high-gain antenna pointed at Earth. If the hydrazine in those lines solidifies, the thrusters cannot fire, the spacecraft cannot maintain its orientation, and the high-gain antenna slowly drifts away from Earth. Communication degrades and eventually ceases entirely. The mission ends not with a dramatic failure, but with a slow, irreversible loss of pointing accuracy that no command from Earth can correct. Hydrazine freezes at approximately 1.6 degrees Celsius. That is barely above the freezing point of water. On Earth, 1.6 degrees Celsius is a chilly autumn morning. On a spacecraft 13 billion miles from the Sun with a fading power supply and no external heat source, 1.6 degrees Celsius is the boundary between a functioning mission and a silent tomb. The hydrazine is stored in a tank inside the spacecraft bus and flows through narrow propellant lines to the thruster assemblies. Those lines are the weakest thermal link. They are thin. They run through areas of the spacecraft that are not well insulated. They are connected to thrusters that are mounted on the exterior of the bus, exposed to the radiative cold of space. If any segment of a propellant line drops below the freezing point, the hydrazine inside it can solidify. A frozen line blocks fuel flow. A blocked line means a thruster cannot fire. And on Voyager 2, some thrusters have already failed due to clogging in their injectors, leaving the spacecraft without backups. Everything is running on what engineers call single string. One set of components. No redundancy. No second chances. By 2014, the situation had become serious enough that the Voyager flight operations team contacted thermal engineers at NASA's Jet Propulsion Laboratory with a specific concern. Propellant line temperatures on Voyager 2 were approaching the hydrazine freezing point. The margin between the measured temperature and the freezing threshold was shrinking with every passing year. If the trend continued, the fuel lines would eventually cross the limit and the mission would end. There was a problem though. The original thermal models of the Voyager spacecraft, the mathematical simulations that predicted how temperatures would behave throughout the vehicle, were nearly 4 decades old. They had been created during the design phase in the 1970s, using tools and assumptions from a different era. Many of the original design documents were incomplete or unavailable. The spacecraft had changed dramatically since launch. Instruments had been turned off. Heaters had been deactivated. Power levels had dropped far below anything the original designers had anticipated. The old models were useless for predicting what was happening inside the spacecraft now. So the thermal engineers did something remarkable. They built a new thermal model from scratch, working with limited temperature telemetry. Because Voyager 2 has very few onboard temperature sensors, they reconstructed the spacecraft's thermal behavior using modern simulation software. They modeled the bus structure, the insulation blankets, the instrument bays, the propellant lines, the thruster assemblies, and the heat paths through the vehicle. They correlated the model against the sparse temperature data the spacecraft was actually sending home, and what they found confirmed the worst fears. Voyager 2's propellant lines in the vicinity of the roll thrusters had already descended to temperatures dangerously close to the hydrazine freezing point. The margin was not comfortable. It was not even adequate by normal engineering standards. It was thin, uncertain, and getting thinner every year. The spacecraft was surviving, but just barely. And every future change in power state, every decision to turn off another heater or shut down another instrument, would shift the thermal balance in ways that had to be carefully predicted before the command was sent. This is the reality of Voyager 2's existence in interstellar space. It is not a spacecraft that happens to be surviving. It is a spacecraft that is being kept alive through continuous, deliberate intervention by a team of engineers on Earth who are managing a thermal budget measured in single-digit watts of margin. Every decision they make carries risk. Turn off the wrong heater, and a propellant line freezes. Turn off the wrong instrument, and the thermal balance inside the bus shifts in an unexpected direction. Leave too many systems running, and the total power draw exceeds what the generators can supply, triggering automatic fault protection that could shut down critical components without warning. The engineers cannot touch the spacecraft. They cannot replace a part, patch a wire, or add insulation. They can only send commands, wait 19 hours for those commands to arrive, and hope that the spacecraft responds correctly. And they have been doing this, successfully, for nearly half a century. There is something else worth understanding about the generators. Something that changes how you think about the spacecraft's future. The plutonium-238 inside the RTGs does not only produce electricity, it produces heat, and it will continue producing heat long after the electrical output drops below usable levels. The thermocouples that convert thermal energy into electricity degrade over time independently of the fuel decay. Their junctions wear out. Their efficiency drops. Eventually, the generators will still be producing thermal energy from plutonium decay, but the thermocouples will be too degraded to convert enough of it into electricity to run anything. When that happens, the spacecraft will have heat but no power. It will be warm, in a sense, at least at the RTG boom, but unable to operate its computers, its transmitter, or any of its instruments. It will be a warm corpse, but that point has not arrived yet. As of 2026, the generators are still producing enough electricity to run the spacecraft's essential systems, though just barely. The margin is razor thin. The engineering team is preparing what may be the most ambitious power-saving maneuver in the history of the mission. A last resort reconfiguration they have been planning for years. The details of that operation and the risks it carries will come later. What matters here is that the maneuver exists at all, that nearly half a century after launch, engineers are still devising new ways to keep a dying machine alive. The Big Bang is not a dramatic maneuver. It is the opposite. It is a meticulous, carefully sequenced shutdown and restart of systems, turning off certain devices and activating lower power alternatives, rearranging how the spacecraft uses its remaining energy so that the most critical functions receive enough power and enough heat to continue. It is the latest in a long series of engineering compromises that have defined the Voyager mission for decades. Each compromise sacrifices something. Each sacrifice buys time. And time is the only currency that matters now. What makes Voyager 2's survival so remarkable is not that it has endured cold, it is that the cold has been managed. Every degree of temperature inside the spacecraft bus is the result of a deliberate decision made by engineers who understand that their power budget will never increase, that their thermal margin will never grow, and that every system they shut down is a system they will almost certainly never turn on again. The spacecraft is being simplified, reduced, stripped down to its most essential functions. It is surviving not by growing stronger, but by becoming less. In 1977, Voyager 2 launched with 10 scientific instruments, multiple heaters, redundant systems, and enough power to run them all simultaneously. Today, it operates 3 instruments. Most of its heaters are off. Its thruster system has no backups. Its voltage is no longer tightly regulated because the power that once fed the voltage regulator's safety circuit has been redirected to keep the science instruments alive. The spacecraft that left Earth was a fully equipped explorer. The spacecraft that exists today is a stripped-down survivor, and every piece that was removed is a piece that an engineer, somewhere, decided the mission could live without. That decision was never easy, and it was never free. Turning off a heater means accepting that the component it protected will get colder. Turning off an instrument means accepting that a measurement no one else in the universe can make will never be made again. Turning off a redundant system means accepting that if the primary system fails, there is no backup. Every sacrifice closes a door that cannot be reopened. But the doors keep closing because the alternative is worse. The alternative is running out of power entirely, triggering an uncontrolled shutdown, freezing the propellant lines, losing antenna pointing, and ending the mission not through a planned sequence of calculated losses, but through a sudden, irreversible systems failure with no possibility of recovery. The engineers chose controlled sacrifice over uncontrolled death, and that choice, repeated dozens of times over decades, is the reason Voyager 2 has not frozen in interstellar space. The physics that makes this possible, the precise mechanics of heat loss in vacuum, the behavior of thermal radiation, the insulation strategies that slow it down, all of that is worth understanding in detail. Because the gap between what people imagine when they hear the word freezing and what actually happens to a spacecraft in interstellar space is enormous. The universe is cold, yes, but it is not cold in the way most people think. And that distinction is the difference between a dead spacecraft and a living one. That is where this story goes next. Most people imagine space as a deep freezer. They picture a spacecraft drifting through the void the way a steak sits in a frozen warehouse, surrounded by relentless cold that attacks from every direction and drains heat with ruthless efficiency. That image feels intuitive. It feels correct, and it is almost entirely wrong. The misunderstanding starts with how we experience cold on Earth. When you walk outside on a winter morning, the air pulls heat from your skin through a process called convection. Moving air molecules collide with your body, absorb thermal energy, and carry it away. The faster the wind blows, the faster you lose heat. That is wind chill. When you grab a metal railing in freezing weather, heat flows from your hand into the metal through direct contact, a process called conduction. Metal is an excellent thermal conductor, so the transfer is rapid and painful. Your body cools because something colder is physically touching it and stealing energy through molecular contact. These two mechanisms, convection and conduction, are responsible for virtually all of the heat loss humans experience in daily life. They are fast. They are aggressive. They are the reason cold feels like an attack, like something actively pulling warmth out of your body. Space has neither. In interstellar space, there is almost no matter. The density of the interstellar medium in the region Voyager 2 currently occupies is measured in particles per cubic centimeter, not billions, not millions. Roughly 1/10 of a particle per cubic centimeter. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The difference between Earth's atmosphere and interstellar space is not a matter of degree. It is a difference so vast that the two environments obey fundamentally different thermal rules. With almost no particles to touch the spacecraft, conduction is essentially zero. There are no air molecules to carry heat away through convection. The two mechanisms that dominate heat loss on Earth simply do not function in the vacuum between the stars. If conduction and convection were the only ways to lose heat, a spacecraft in interstellar space would never cool down at all. It would retain whatever thermal energy it carried indefinitely, like a perfectly sealed container that nothing can enter or leave. But there is a third mechanism, thermal radiation, and this is the only way Voyager 2 loses heat. Every object in the universe that has a temperature above absolute zero emits electromagnetic radiation. This is not optional. It is not something that requires a special surface or a particular material. It is a fundamental law of physics. The atoms in any object vibrate, and those vibrations produce photons, particles of light, that carry energy away from the surface. The warmer the object, the more energetic the photons, and the faster the energy leaves. This is described by a relationship called the Stefan-Boltzmann law, which states that the total energy radiated by an object is proportional to the fourth power of its temperature. That fourth power relationship matters enormously. It means that a hot object radiates heat much faster than a warm object. A spacecraft that is 200 degrees Celsius will radiate heat far more rapidly than one at 20 degrees Celsius. But it also means that as an object cools down, its rate of heat loss slows. The cooler it gets, the less energy it radiates, and the slower it continues cooling. This creates a natural braking effect. A spacecraft in vacuum does not plunge toward absolute zero the way a glass of water freezes in a kitchen freezer. It approaches a temperature equilibrium, a balance point where the heat it generates internally equals the heat it loses through radiation. This equilibrium is the key to Voyager 2's survival. The spacecraft does not need to fight off an aggressive assault of cold. It needs to maintain an internal heat source large enough to offset its radiative losses. As long as the heat flowing into the spacecraft bus exceeds the heat radiating outward, the interior stays above freezing. The moment the balance tips, temperatures drop. But the drop is gradual, not sudden. Radiation is a patient thief, not a violent one. Think of it this way. Imagine sitting next to a campfire in the middle of a vast snowfield on a windless night. There is no breeze to strip heat from your body. The snow is not touching you, so conduction is minimal. The fire radiates warmth toward you, and your body radiates warmth outward into the cold sky. As long as the fire burns, you stay warm. The snowfield is cold, enormously cold, but it cannot aggressively pull the heat from you the way a blizzard would. The fire sets your temperature, not the snow. If the fire shrinks, you get colder. If it dies, you eventually radiate all your warmth into the sky and reach the temperature of your surroundings. But the cooling is slow, governed by radiation alone, and it takes far longer than most people would guess. Voyager 2's plutonium is the campfire, the interstellar medium is the snowfield, and the multi-layer insulation wrapped around the spacecraft is like a reflective blanket that sends much of your radiated heat back toward your body, drastically reducing how much fire you need to stay warm. That insulation deserves serious attention, because it is one of the least celebrated and most important engineering decisions in the entire Voyager program. Multi-layer insulation is not a single material. It is a stack of thin, reflective sheets, typically made from Kapton or mylar, separated by low-conductivity spacer materials. Each layer reflects a large fraction of the thermal radiation hitting it. A photon emitted by the warm spacecraft bus strikes the first layer and roughly 95% of its energy is reflected back inward. The small amount that passes through strikes the second layer, and 95% of that is reflected back. Then the third layer, then the fourth. Stack enough layers together, and the total heat escaping through the blanket drops to a tiny fraction of what the bare surface would radiate. Voyager's bus is wrapped in these blankets. The result is that the spacecraft's internal temperature is determined overwhelmingly by how much electrical power is being dissipated inside the bus, not by the temperature of the surrounding environment. If interstellar space were 5 Kelvin instead of 2.7 Kelvin, it would make almost no practical difference to Voyager 2's internal temperatures. The insulation is so effective that the external environment is nearly irrelevant. What matters is the internal heat source. This is the single most important concept in understanding why Voyager 2 has not frozen. The spacecraft is not fighting external cold, it is managing internal heat. The danger is not that space is too cold. The danger is that the spacecraft is generating less and less warmth as its power supply decays, and eventually the internal heat will not be enough to offset radiative losses through the insulation. The enemy is not the void, the enemy is the clock. Now, here is where the physics becomes more specific and more painful. Recall the numbers from earlier. Each of Voyager 2's 3 RTGs produced approximately 2400 watts of thermal power from plutonium decay, but only converted roughly 6.5% of that into electricity. The vast majority of the thermal energy, more than 93%, was rejected as waste heat through the generator's cooling fins. Those fins are mounted on a boom, extending away from the spacecraft body specifically so that the enormous thermal output of the plutonium does not overwhelm the electronics. The generators were deliberately placed far from the bus and oriented to dump their waste heat into space, because during the early mission, that heat would have cooked sensitive instruments. This means the RTGs themselves do not significantly heat the spacecraft bus. Their waste heat escapes through the fins and is gone. The heat that keeps the bus warm comes exclusively from the electricity that flows into it. When that electricity powers a heater, the heater converts it into thermal energy inside the bus. When it powers a computer, the computer's circuits produce heat as a byproduct. When it flows through wiring and voltage regulators, those components generate tiny amounts of warmth. In every case, the electrical energy entering the bus eventually becomes thermal energy trapped inside the insulated structure. The spacecraft's internal temperature is a function of how many watts of electricity are being consumed inside the bus at any given moment. At launch, 470 watts of electricity flowed into the spacecraft. All of it was eventually converted into heat inside the bus or radiated outward through the antenna. The insulation was designed so that this level of internal heating, combined with supplemental heaters running on dedicated power, would keep all components within their safe operating temperature ranges, even as far from the Sun as Neptune. But the designers did not design Voyager 2 to operate at 143 astronomical units from the Sun, with only 220 watts of power. They did not design it to function with most of its heaters turned off. They did not design it to maintain survivable propellant line temperatures on less than half its original energy budget. The fact that it is doing all of these things is a testament to how much thermal margin the original design contained, and how skillfully engineers have managed the decline. Understanding why the margin existed requires understanding what the designers were actually worried about. When Voyager 2 was being built in the mid-1970s, the thermal engineers faced a dual challenge. Near the Sun, during the early phases of the mission, the spacecraft would receive intense solar heating. The electronics bus could overheat, so the thermal louvers on the bus were designed to open and vent excess heat when internal temperatures climbed too high. But at the outer planets, billions of miles from the Sun, solar heating would be negligible. The spacecraft would rely almost entirely on its internal electrical systems for warmth. The insulation had to be good enough to retain that heat against radiative losses in the cold of deep space. The designers built for the cold case. They made the insulation thick enough and reflective enough to keep the bus warm at Saturn, the farthest confirmed destination in the original mission plan. When the mission was extended to Uranus and then Neptune, the spacecraft pushed further into cold that the original design had to absorb with fewer watts of sunlight and slightly less RTG power. It managed because the margins were generous. The thermal design was conservative. It had been built to handle uncertainty, and that conservatism is what has kept Voyager 2 alive decades past its expected lifetime. But conservatism has limits. Every year, 4 watts of electrical power disappear. 4 watts of internal heating vanish from the bus. The insulation does not change. The radiative losses do not change significantly, but the heat source shrinks. The equilibrium temperature inside the bus drops slightly every year. Components that were comfortably warm in 1989 are merely tolerable now. Components that were tolerable in 2010 are approaching their minimum rated temperatures, and the propellant lines, the most thermally vulnerable part of the entire spacecraft, are brushing against the freezing point of hydrazine. Here is a detail that makes the thermal situation even more counterintuitive. Interstellar space, despite being among the coldest environments in the universe, is actually slightly warmer in one specific sense than the deep space Voyager 2 passed through on its way out of the solar system. The cosmic microwave background radiation, the afterglow of the Big Bang, fills all of space with a faint bath of photons, corresponding to a temperature of about 2.7 Kelvin. That is roughly minus 270 degrees Celsius. In the outer solar system, far from any star or planet, the ambient radiation environment is dominated by this same background. The temperature of the surroundings has been essentially constant for Voyager 2's entire journey, but the interstellar medium itself, the thin gas between the stars, has a temperature that is surprisingly high by certain measures. The plasma that Voyager 2 is now moving through has a measured temperature of tens of thousands of Kelvin in some regions. This sounds absurd. How can the space around the spacecraft be tens of thousands of degrees while the background is near absolute zero? The answer is that temperature and heat are not the same thing. Temperature is a measure of the average kinetic energy of individual particles. In the interstellar medium, the particles, mostly ionized hydrogen, are moving extremely fast. Each individual proton or electron carries substantial kinetic energy. By the definition of temperature, the gas is very hot, but there are almost no particles. The density is so low that even though each particle is energetic, the total amount of thermal energy in any given volume is vanishingly small. If you could somehow stand in this gas, you would not feel warmth. The particles would strike you so rarely that their collective heating effect would be unmeasurable. A cubic meter of interstellar medium at 50,000 Kelvin contains less total thermal energy than a cubic meter of room temperature air on Earth. The gas is hot in the physics sense, but carries almost no heat in the practical sense. This means the interstellar medium does not warm Voyager 2 in any meaningful way. The spacecraft does not absorb significant heat from its surroundings. The energy balance remains almost entirely internal. Heat in, from electrical power. Heat out, through radiation. Nothing outside the spacecraft contributes or subtracts in any significant amount. The probe is thermally isolated, enclosed in its insulation, dependent on its own fading power supply, and answerable to no external thermal influence. This isolation is both a blessing and a curse. It is a blessing because it means the spacecraft is not being actively cooled by its environment. Space is not sucking heat out of Voyager 2 the way cold water sucks heat out of a swimmer. It is a curse because it means there is no external source of energy to supplement the failing RTGs. In the inner solar system, a spacecraft can absorb sunlight. Near a planet, it can receive reflected or emitted infrared radiation. In interstellar space, there is nothing. The spacecraft is alone with its plutonium, and the plutonium is fading. There is another subtlety worth understanding. The RTGs themselves are still producing substantial thermal power from plutonium decay, even though their electrical output has dropped below half of the original level. Remember, the thermocouples that convert heat into electricity degrade independently of the fuel. The plutonium-238 is still decaying, still releasing alpha particles, still generating thermal energy. After roughly half a half-life, approximately 44 years, the thermal output of the fuel has decreased by a calculable fraction, but it is still substantial. Each generator is still producing well over 1,000 watts of thermal power, but almost none of that thermal power reaches the spacecraft bus. It radiates away through the cooling fins on the RTG boom, exactly as designed. The generators were deliberately placed far from the bus and oriented to reject their waste heat into space, because during the early mission, that enormous heat output would have cooked the electronics. The separation that protected the spacecraft near Jupiter now works against it in interstellar space. The RTGs are radiating kilowatts of heat into the void, while the bus struggles to stay warm on 220 watts of electrical dissipation. You might wonder, could engineers redirect some of that waste heat into the bus? Could they pipe it back along the boom to warm the propellant lines? The answer is no. There is no mechanism aboard the spacecraft to do this. No heat pipes were installed between the RTG boom and the bus. No thermal connections exist. The design assumed the spacecraft would always have enough electrical power to keep itself warm through internal dissipation. It did not anticipate a scenario where the generators would still be producing thermal energy, but the bus would be starving for warmth. The architecture of the spacecraft makes it impossible to use the one abundant resource it still possesses. This is one of the great ironies of Voyager 2's situation. It is a spacecraft that still carries a source of substantial heat. The plutonium has not run out. It will not run out for decades, but the heat is in the wrong place, separated from the electronics by a boom and a vacuum gap that cannot be bridged. The spacecraft will eventually lose its ability to function not because it lacks heat, but because it lacks the electrical power to deliver that heat where it is needed. And that brings the thermal story back to the engineering team on Earth. Because the physics of heat loss in vacuum, the behavior of multi-layer insulation, the nature of radiative equilibrium, all of these factors create a situation that is manageable, but only through extremely careful intervention. The spacecraft is not dying from exposure. It is dying from a slow, predictable reduction in the power available to keep its core systems above minimum operating temperatures. The physics allows survival. The insulation provides protection. The plutonium still decays, but the margin between survival and failure is measured in single watts, and that margin shrinks every year. Every time an engineer at JPL decides to shut down a heater, they are not simply saving power. They are changing the thermal profile of the entire spacecraft bus. Heat that was being generated in one location vanishes. Components nearby cool down. The temperature distribution shifts. Sometimes the shift is predictable. Sometimes it is not. The thermal model built from scratch in 2014 helps, but it is a model, not a crystal ball. Its predictions depend on assumptions about material properties and heat paths that may have shifted over decades of radiation exposure and thermal cycling. It makes assumptions about material properties that may have changed after decades of radiation exposure. It cannot perfectly predict what happens when a specific heater on a specific propellant line is turned off for the first time in 40 years. And yet the engineers have been making these decisions successfully for decades. They have turned off heaters and monitored the results. They have shut down instruments and watched the thermal balance shift. They have pushed the spacecraft closer and closer to its limits, and it has continued to function, not because they were lucky, but because they were careful, because they understood the physics, because they built models and checked them against reality and refined them when the data came in. The physics of heat loss in vacuum is unforgiving but simple. Objects radiate heat proportional to the fourth power of their temperature. Insulation reduces radiative losses. Internal power provides heating. The equilibrium temperature is set by the balance between these factors. There is no mystery in the equation. There is no hidden variable. The spacecraft's temperature at any moment can, in principle, be calculated from first principles if you know the power input and the thermal properties of every surface. What makes Voyager 2's survival remarkable is not the physics. The physics is textbook material. What makes it remarkable is that humans have managed the declining power budget so precisely, for so long, with so little margin for error, communicating through a 19-hour time delay with a spacecraft they can never touch. Using a thermal model they had to build from scratch nearly 4 decades after launch, because the original one no longer existed. The physics permits survival. The insulation enables survival. But the engineering makes survival real, and that engineering is a story of sacrifice, of choosing what dies so that the rest can live, of accepting permanent loss as the price of continued existence. That story, the specific sequence of shutdowns and compromises and hard choices, is where the real drama lives. And that is where this journey goes next. Voyager 2 launched with 10 scientific instruments. Each one was a marvel of 1970s engineering, custom built for specific measurements that no spacecraft had ever attempted at the outer planets. The imaging science subsystem carried wide-angle and narrow-angle cameras that would photograph Jupiter's swirling storms, Saturn's rings, the cracked surface of Miranda at Uranus, and the frozen geysers of Triton at Neptune. The infrared spectrometer measured heat radiation from planetary atmospheres. The ultraviolet spectrometer studied atmospheric composition. The photopolarimeter subsystem analyzed light scattered by planetary surfaces and rings. The plasma science instrument sampled the charged particles of the solar wind. The low-energy charged particle instrument detected ions and electrons in planetary magnetospheres. The cosmic ray subsystem measured high-energy particles from beyond the solar system. The magnetometer recorded the magnetic fields of every planet the spacecraft encountered. The plasma wave subsystem listened for electrical oscillations in the space around the probe. And the planetary radio astronomy experiment used the spacecraft's antenna to study radio emissions from the giant planets. 10 instruments. 10 windows into worlds no human had ever seen up close. And one by one, over the course of decades, nearly all of them have been shut down. The shutdowns did not begin as emergencies. The earliest ones were logical. After Voyager 2 completed its flyby of Neptune in 1989, the cameras were no longer needed. There were no more planets to photograph. The imaging science subsystem was turned off. The infrared spectrometer followed. The ultraviolet spectrometer went next on Voyager 2, though it stayed on longer aboard Voyager 1, for a specific scientific reason. The planetary radio astronomy experiment had no planets left to listen to. These instruments were designed for the Grand Tour, and the Grand Tour was over. The photopolarimeter subsystem was the first science instrument formally shut down on Voyager 2 in 1991. It saved 1.2 watts. That number is worth pausing over. 1.2 watts, less than the power consumed by a single small LED light. That is how thin the margins had already become by the early 90s. 1.2 watts was significant enough to justify permanently silencing a scientific instrument. The SCAN platform that housed several of the outward-looking instruments was eventually powered down entirely on Voyager 2. The platform itself had a motor that consumed power just by being energized, and with no instruments left to point, the power was needed elsewhere. Each shutdown followed the same bleak arithmetic. How many watts does this system consume? What do we lose if we turn it off? What do we gain? Is the gain worth the loss? The answer was almost always yes, because the alternative was losing everything. Through the 1990s and 2000s, the remaining instruments were the ones relevant to the Interstellar mission. The plasma science instrument measured the properties of the solar wind and, later, the interstellar plasma. The low-energy charged particle instrument detected ions and electrons at various energy levels. The cosmic ray subsystem tracked high-energy particles arriving from across the galaxy. The magnetometer measured the magnetic fields threading through interstellar space. And the plasma wave subsystem listened for oscillations in the electron density of the surrounding medium. These 5 instruments were the reason the mission still existed. Everything else had been stripped away, but even these survivors were living on borrowed time, because the instruments were not the only systems consuming power. Heaters were running throughout the spacecraft bus, small electrical devices whose sole purpose was to keep specific components above their minimum operating temperatures. Some heaters protected instrument electronics, others warmed propellant lines, others kept the spacecraft's command computer or flight data subsystem within safe ranges. Each heater consumed a few watts, and each few watts mattered. The heater shutdowns began before the instrument shutdowns and continued in parallel. Engineers would examine the thermal model, identify a heater protecting a component that had some temperature margin remaining, and turn it off. The component would cool, sometimes by a few degrees, sometimes by more. If the cooling stabilized above the minimum allowable temperature, the shutdown was considered successful. If temperatures approached dangerous levels, engineers had to consider whether to restore the heater, which meant sacrificing power somewhere else, or accept the risk and hope the component could tolerate the cold. Some of these decisions worked out better than expected. Components designed to operate within a specified temperature range sometimes proved capable of functioning well outside that range. Electronics rated for a minimum of 0 degrees Celsius continued working at -10 or even lower. The spacecraft's hardware had been built with engineering margins that the designers themselves may not have fully appreciated. Decades of operation at gradually declining temperatures provided a slow-motion stress test that revealed hidden resilience in the components. Other decisions carried genuine risk. Components that survived beyond their rated temperature ranges did not always emerge unscathed. Sensors drifted out of calibration. Instruments developed quirks that had to be diagnosed across a 19-hour communication delay. Engineers learned to distinguish between degradation that was tolerable and degradation that threatened the mission, a judgment that required intimate knowledge of hardware that had been operating continuously for longer than many of the engineers had been alive. By 2014, propellant line temperatures on Voyager 2 had descended to the edge of the hydrazine freezing point. The thermal model built that year gave engineers a tool they had been lacking, a way to predict how the spacecraft's internal temperatures would respond to specific power state changes. But the model also confirmed what everyone already suspected. The trend was going in only one direction. Every year the bus got colder. Every heater shutdown accelerated the cooling. And the most critical temperature boundary, the hydrazine freezing point at approximately 1.6 degrees Celsius, was approaching with quiet certainty. What happens inside JPL when these decisions are made deserves more attention, because the process is not automatic. It is not algorithmic. It is a negotiation between the science team and the engineering team, mediated by thermal models, power projections, and the kind of institutional knowledge that only accumulates over decades of working with a single spacecraft. The science team wants every instrument to keep running as long as possible. Every operating instrument collects data that no other facility in the world can replicate. The magnetometer measures interstellar magnetic fields with a sensitivity and a vantage point that cannot be achieved from Earth. The plasma wave subsystem detects electron density oscillations in the interstellar medium, providing direct measurements of conditions in a region that ground-based astronomers can only model indirectly. Losing any instrument means losing access to a type of information that may not be available again for decades, if ever. The science team fights for every watt. The engineering team has a different mandate. Their job is to keep the spacecraft alive. Not just the instruments, but the bus, the computer, the transmitter, the thrusters, the propellant lines. If the spacecraft dies, all the instruments die with it. The engineering team thinks in terms of thermal margin and power budget and failure modes. They know exactly how many watts each system draws, exactly how much heat each component produces, exactly how close each propellant line is to the freezing threshold, and they know that a single miscalculation can end the mission permanently. When a shutdown decision must be made, the two teams sit down together. The thermal model is consulted. Engineers run simulations showing what happens to the bus temperature distribution if a specific heater is turned off or a specific instrument is deactivated. They examine where the freed power will go. If a heater protecting a propellant line near the roll thrusters is turned off, how much will that line cool? How long before it reaches the allowable flight temperature limit? Can the power saved by turning off that heater be redirected to a load inside the bus that generates heat in a more useful location? Warming the coldest area through indirect thermal conduction? These trade-offs are not simple. The spacecraft bus is a three-dimensional structure with complex heat paths. Turning off a heater on one side of the bus does not necessarily cool, only the components next to it. Heat flows through the aluminum honeycomb structure, through mounting brackets, through wiring harnesses. A change in one location can shift temperatures throughout the vehicle in ways that are difficult to predict without a detailed model. The thermal engineers run cases. They vary assumptions. They present the science team with options. If we turn off this heater, we gain 3 watts, and the nearest propellant line cools by approximately 2 degrees over the next 6 months. If we turn off this instrument instead, we gain 5 watts but lose the ability to measure cosmic ray flux. The science team weighs the scientific cost. The engineering team weighs the survival risk. And then a decision is made. Sometimes unanimously, sometimes not, but always with the understanding that whichever option is chosen, the decision is irreversible. The heater will not be turned back on. The instrument will not be restarted. The spacecraft will be permanently simpler after the command is sent. The commands themselves require their own careful choreography. A shutdown sequence for a science instrument is not a single off switch. It involves multiple commands sent over hours, each one verified before the next is transmitted. The 19-hour communication delay means that if something goes wrong during the sequence, the team will not know about it until nearly a day later. So the sequences are designed with built-in checkpoints. Send a command. Wait for confirmation that the spacecraft received and executed it. That confirmation takes 38 hours to complete the round trip, 19 hours out and 19 hours back. Only after confirmation is received does the next command go out. A full instrument shutdown can take days or even weeks when measured in ground time. The team cannot rush it. They cannot skip steps. They cannot assume that a command was received just because it was sent. Every action is deliberate, every step verified, because a mistake at this distance is a mistake that may never be corrected. These command sequences are also vulnerable to the sheer distance involved. A signal crossing 13 billion miles of space is not immune to degradation. Cosmic ray strikes can flip bits in transit. The spacecraft's aging receiver can misinterpret instructions. In November 2006, a routine command sent to Voyager 2 was incorrectly decoded by the onboard computer as an instruction to activate the magnetometer heaters. That single corrupted command kept the heaters running for 5 days, driving the sensor temperature above 130 degrees Celsius, far beyond its design limits. The magnetometer survived, but the incident revealed a vulnerability that no protocol can fully eliminate. When a single misread bit can overheat an instrument or misalign an antenna, every transmission becomes an act of controlled faith. The engineering team cannot guarantee that commands arrive intact. They can only design sequences robust enough to tolerate errors and build in verification steps that catch problems before they cascade. The process also demands that the team account for the spacecraft's age in ways that go beyond power budgets. Voyager 2's onboard memory totals 68 kilobytes across all of its computer systems. That is less storage capacity than a single modern digital photograph. Every command sequence, every software routine, every fault protection algorithm must fit within that constraint. When engineers design a new operating procedure, they are writing software for a machine with less computational power than a basic calculator, then transmitting it across 13 billion miles and hoping the aging memory cells store it correctly. Radiation exposure over nearly 5 decades has degraded some of those memory cells. Stored values can drift. Instructions that were reliable a decade ago may behave unpredictably today. The engineering team tests every upload exhaustively on ground-based simulators that replicate the spacecraft's hardware before committing a single command to the Deep Space Network for transmission. The thruster software patch is a case study in this painstaking process. The patch modifies the firing profile of the remaining attitude control thrusters, adjusting pulse durations and intervals to reduce the rate at which residue accumulates in the injector nozzles. Every instruction must account for the possibility that the upload is corrupted in transit, that a cosmic ray strike flips a bit during reception, that the aging hardware does not execute the new routine as designed. As with every major procedure, the patch will be tested on the nearer spacecraft first before being attempted on Voyager 1. If the patch works, it will be applied to Voyager 1. If it fails, the consequences must be contained. Nothing about this process is casual. Nothing is taken for granted. Every operation on a 49-year-old spacecraft, 13 billion miles away, is treated as though it could be the last. The engineers responded the only way they could. They turned off more things. But by the early 2020s, the easy cuts had already been made. There were no more surplus heaters to sacrifice. Every heater still running protected something that mattered. Every instrument still operating collected data that no other spacecraft in the universe could provide. The next round of shutdowns would cost something real, not just convenience or redundancy, but actual scientific capability. In October 2024, NASA announced that the plasma science instrument on Voyager 2 had been turned off. This instrument had measured charged particles in the solar wind for decades and had played a critical role in confirming Voyager 2's crossing of the heliopause into interstellar space in 2018. Its measurements of the interstellar plasma were scientifically valuable and entirely unique. No other instrument on any other spacecraft could replicate them. Turning it off meant that particular window into the interstellar medium closed permanently. Then in March 2025, the low-energy charged particle instrument on Voyager 2 was powered down. This instrument had been operating almost without interruption since launch, nearly 48 years. Its rotating sensor platform was driven by a stepper motor that had been tested for 500,000 steps, enough to guarantee operation through the Saturn encounter. By the time it was deactivated, that motor had completed more than 8.5 million steps. It had exceeded its design specifications by a factor of 17. The instrument was not failing, it was still collecting data. It was turned off because its power was needed elsewhere. The motor on the low-energy charged particle sensor was left running at half a watt, a tiny expenditure, because keeping it active gives engineers the faintest possibility of turning the instrument back on someday, if additional power can be found. That half-watt decision captures the entire philosophy of the Voyager mission in miniature. Do not close a door completely. If leaving it open a crack costs almost nothing. The cosmic ray subsystem on Voyager 2 is scheduled for shutdown in 2026. After that, only 2 instruments will remain active, the magnetometer and the plasma wave subsystem. 2 instruments out of the original 10. 2 narrow channels of information still flowing from a spacecraft that once carried a full suite of planetary science tools. This progressive reduction tells a story that goes beyond engineering. Voyager 2 is being pared down to the leanest configuration that can still return meaningful data. What once carried 10 instruments and a full suite of heaters now operates on a handful of surviving systems, each one kept alive only because something else was allowed to go dark. Think of an old car that keeps running not because you maintain it in perfect condition, but because you strip away everything non-essential. The air conditioning goes first, then the radio, then the passenger seats, then the body panels. Eventually you are driving a bare frame with an engine and a steering wheel, and even the engine is burning its last drops of fuel. The car still moves, it still carries you forward. But it is no longer the machine that rolled off the assembly line. It is a survivor, defined not by what it has, but by what it has lost. Voyager 2 is that machine, and the people deciding what to remove next carry a burden that few engineers in history have ever faced. Every decision they make is permanent. There is no warehouse of spare parts. There is no service mission. The spacecraft is more than 13 billion miles away, traveling at roughly 34,000 miles per hour in the opposite direction from Earth. Whatever they turn off stays off. Whatever capability they sacrifice is gone forever. Suzanne Dodd, the Voyager project manager at JPL, put the stakes plainly. If the team does not turn off instruments now, the spacecraft would have only a few more months of power before they would need to declare end of mission. That is the arithmetic. Shut down one instrument and gain a year. Shut down another and gain another year. Keep going until there is nothing left to shut down, and then the mission ends. The only question is how long the sequence can be stretched. The voltage regulator gambit of 2023 was one of the more creative moves in this sequence. Engineers discovered that a small reservoir of backup power had been set aside within the spacecraft's voltage regulation system. This power was reserved for a safety mechanism designed to protect instruments against voltage fluctuations. If the spacecraft's electrical output from the RTGs varied unexpectedly, the regulator would tap this reserve to stabilize the voltage and prevent damage to sensitive electronics. The engineering team realized that after more than 45 years of flight, the spacecraft's electrical system had remained remarkably stable. Voltage fluctuations had been minimal. The safety margin that the backup power was protecting against had, in practice, never been needed. So they made a calculated decision. They redirected that backup power into the main electrical bus, accepting the slightly increased risk of unregulated voltage, in exchange for enough additional watts to keep all 5 remaining science instruments running for approximately 3 more years. The decision was not made lightly. Variable voltages can damage instruments. A sudden spike could fry a circuit board that has been operating in deep space for nearly half a century, but the team assessed the risk and concluded it was small. The generators had been stable, the electrical system had proven reliable, and the alternative, shutting down a science instrument immediately, meant losing data that could never be recovered. The reward outweighed the risk. The backup power was tapped, the instruments kept running, and the engineers added another entry to the long list of compromises that have defined this mission. Now, in 2026, the team is preparing for the most ambitious power-saving maneuver yet. They call it the Big Bang. The name sounds dramatic, but the operation itself is the opposite of dramatic. It is meticulous, cautious, and painfully slow. The Big Bang involves shutting down a group of powered devices simultaneously and activating lower power alternatives in a carefully choreographed sequence. The goal is to reconfigure how the spacecraft uses its remaining energy, creating a new sustainable power equilibrium that keeps the most critical systems alive while drawing fewer total watts. Some components will be turned off permanently, others will be replaced by less power-hungry alternatives that provide reduced functionality. The overall effect is to lower the spacecraft's power floor, the minimum number of watts needed to maintain basic operations, and create a small buffer of surplus power that can sustain the remaining science instruments for additional months or years. Voyager 2 will serve as the test vehicle. It has slightly more available power than Voyager 1 and is closer to Earth, which means the communication delay is shorter and troubleshooting is faster. Testing is planned for May and June of 2026. If the reconfiguration succeeds on Voyager 2, the team will attempt the same procedure on Voyager 1 no sooner than July. The Big Bang carries real risk. Turning off multiple systems simultaneously on a 49-year-old spacecraft 13 billion miles away is not something anyone does casually. If a critical system fails to restart after the reconfiguration, there may not be enough power to recover it. If the thermal balance shifts unexpectedly during the transition, propellant lines could cool below the freezing threshold before engineers even learn something went wrong. The 19-hour communication delay means that by the time a problem is detected on Earth, it has already been a problem on the spacecraft for nearly a full day. Corrective commands will take another 19 hours to arrive. Almost 2 full days can pass between a failure and a response. In that time, the spacecraft is on its own, but the alternative to the Big Bang is the same alternative that has driven every previous shutdown decision. Without the reconfiguration, the power supply will continue declining at 4 watts per year, and the team will be forced to shut down instruments one by one until nothing is left. The Big Bang is an attempt to break that pattern, to find a way to stretch the remaining power further by operating the spacecraft in a fundamentally different mode than it has ever operated in before. There is a detail about the communication link that adds another layer of difficulty. Voyager 2's high-gain antenna must remain pointed at Earth with extreme precision for the signal to be received by the Deep Space Network. The spacecraft uses its hydrazine thrusters to maintain this orientation, firing small corrective bursts whenever it drifts. But some of those thrusters have experienced clogging in their fuel injectors. The tiny nozzles through which hydrazine flows have become partially blocked, likely by residue buildup over decades of use. Backup thrusters that could have taken over are also compromised. The spacecraft has no fallback if another thruster fails, a reality the engineering team has been forced to accept as backups were exhausted one by one over the decades. NASA has also been developing a software patch to modify thruster behavior, adjusting firing profiles to slow the clogging that has already disabled some of the spacecraft's backup nozzles. The details of how that patch is designed, tested, and transmitted reveal just how painstaking every intervention on Voyager 2 has become. The thruster problem intersects with the thermal problem in a critical way. If the thrusters fail, the antenna drifts. If the antenna drifts, communication is lost. If communication is lost, engineers cannot send commands. If they cannot send commands, they cannot manage the power budget. If they cannot manage the power budget, the thermal balance shifts uncontrolled. Systems cool, propellant lines freeze, the spacecraft goes silent permanently. In July 2023, exactly this scenario nearly occurred. A programming error caused Voyager 2's high-gain antenna to shift 2 degrees away from Earth. 2 degrees does not sound like much, but at a distance of 13 billion miles, even a tiny angular error means the signal misses the receiving dishes entirely. Communication was lost. For nearly 2 weeks, engineers could not reach the spacecraft. On August 1st, they detected a faint carrier signal using multiple antennas of the Deep Space Network. On August 4th, the Canberra station in Australia sent a high-power transmission, essentially shouting across 13 billion miles of space, commanding the spacecraft to reorient toward Earth. The command worked. Communication was restored, but the incident demonstrated how thin the thread had become. One software glitch, one misaligned antenna, one frozen thruster, and the mission could end without warning. The spacecraft also carries an autonomous failsafe. If communication with Earth is lost for an extended period, Voyager 2 is programmed to automatically reset its antenna orientation to point toward Earth. This backup routine would have activated by October 2023 if the August recovery had failed, but the failsafe itself depends on functioning thrusters, which depend on liquid hydrazine, which depends on propellant line temperatures remaining above the freezing point. Every system depends on every other system. The interdependencies are absolute. There is one more piece of the survival puzzle that is easy to overlook. Voyager 1 launched 16 days after Voyager 2, but on a faster trajectory, is farther from the Sun and from Earth. You would expect it to be colder. It is not. Voyager 1 is actually the warmer of the 2 spacecraft. And the reason is a small but consequential decision made nearly half a century ago. After Voyager 2 launched in August 1977, engineers monitoring its telemetry noticed that the spacecraft was running colder than thermal models had predicted. Something about the actual thermal performance of the bus did not match the design calculations. The temperatures were not dangerously low, but they were lower than expected, and the discrepancy suggested that the spacecraft's insulation was slightly less effective than assumed, or that heat was escaping through pathways the models had not fully accounted for. Voyager 1 had not yet launched. It was scheduled for September, 16 days later. That small window of time gave the engineering team an opportunity. They added extra insulation to Voyager 1 before it left the ground. The modification was minor, a small change in the thermal blanket configuration, but it was enough to improve heat retention inside the bus. When Voyager 1 launched and headed outward on its faster trajectory past Jupiter and Saturn and into interstellar space, it carried that extra insulation with it. Today, nearly 5 decades later, that small pre-launch adjustment is still paying dividends. Voyager 1, despite being farther from the Sun and deeper into interstellar space, maintains slightly higher internal temperatures than Voyager 2. It has slightly more thermal margin. Its propellant lines are slightly further from the freezing point. That difference, originating in a decision made in a matter of days in 1977, may ultimately determine which spacecraft survives longer. Voyager 2 never got that extra insulation. It flies colder, its margins are thinner, its propellant lines are closer to the edge. The engineers managing it today work with less room for error than their counterparts managing Voyager 1, and both teams are working with almost no room at all. This is the cumulative picture of Voyager 2's survival. It is not a single engineering triumph. It is a chain of hundreds of decisions, stretching across decades, each one trading something permanent for something temporary. A heater sacrificed for a few watts, an instrument silenced for a few years, a safety margin bypassed for a few more months of science, a voltage regulator raided for its backup power, a thruster patched with software because the hardware can never be touched. Each decision is a small death. Each small death buys a small extension of life. The spacecraft shrinks. Its capabilities narrow. Its options diminish. It becomes less than what it was, not because it is failing, but because it is being deliberately reduced by the people who care about it most. The engineers are not watching Voyager 2 die, they are managing its decline, choosing which parts of it to let go so the essential core can persist a little while longer. The mathematics of this decline are merciless. 4 watts per year, every year, with no possibility of reversal. The RTGs will never produce more power than they did yesterday. No new energy source will be delivered, no repair crew will arrive. The trajectory of the power curve is fixed, and it points in one direction, down. Every strategy the team has devised, the heater shutdowns, the instrument sacrifices, the voltage regulator trick, the Big Bang reconfiguration, these are not solutions, they are delays. They push the endpoint further into the future, but they do not change the shape of the curve. Eventually, the power will drop below the threshold needed to run even one instrument, to keep even one propellant line above freezing, to transmit even a carrier signal back to Earth. The question is not whether that day will come, the question is when, and the answer to that question depends on how many more small deaths the engineers can find, how many more pieces of Voyager 2 can be sacrificed, how many more compromises can be made before there is nothing left to compromise. That future, the timeline of Voyager 2's final years, and the immense silence that follows, is where this journey ends. The spacecraft will not vanish when it stops talking. It will keep moving, keep coasting, keep carrying the golden record through the interstellar medium for thousands of centuries. But its voice will be gone. The conversation between a machine and its makers, sustained across 13 billion miles by ingenuity and stubbornness and loss, will end. And when it does, the silence will be permanent. That is where this journey goes now. Somewhere in the early to mid-2030s, a signal will stop. It will not stop dramatically. There will be no explosion, no collision, no sudden catastrophe. One day, the engineers at JPL will send a command to Voyager 2 and receive no response. Or they will notice that the faint carrier signal they have been tracking, a simple tone confirming the spacecraft's continued existence, has dropped below the noise floor of the Deep Space Network's most sensitive receivers. They will try again. They will listen harder. They will aim every available dish at the patch of sky where Voyager 2 should be, straining to pick up the whisper of a transmitter broadcasting at roughly 23 watts from a distance that by then may exceed 160 astronomical units. And eventually, after days or weeks of silence, someone will make the determination. The mission is over. The exact date cannot be predicted. Too many variables remain unknown. How quickly will the remaining RTG thermocouples degrade? Will the Big Bang reconfiguration of 2026 succeed in freeing enough power to extend operations? Will the propellant lines survive another winter and another after that? Will a thruster clog, an antenna drift, a computer glitch cascade into something unrecoverable? The engineers working the mission today believe that at least one science instrument on Voyager 2 could remain operational into the early 2030s. That is their best estimate, informed by decades of experience managing the spacecraft's decline, but they are the first to acknowledge that any day could be the last. Linda Spilker, the Voyager project scientist at JPL, captured this reality with a single statement. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last. But that day could also bring another interstellar revelation. So we are pulling out all the stops, doing what we can to make sure Voyagers 1 and 2 continue their trailblazing for the maximum time possible. The maximum time possible. That phrase contains the entire emotional weight of the mission's final chapter. Not the maximum time desired, not the maximum time imagined, the maximum time possible. The word acknowledges a boundary. The power curve has a flaw. The thermal margin has a limit. The hydrazine has a freezing point. And all of these boundaries are converging, slowly, inevitably, on the same outcome. Here is what the final years will likely look like, based on current projections and NASA's published plans. After the cosmic ray subsystem is shut down on Voyager 2 in 2026, 2 instruments will remain: the magnetometer, which measures the strength and direction of the interstellar magnetic field, and the plasma wave subsystem, which detects oscillations in the electron density of the interstellar medium. These 2 instruments are the final scientific eyes and ears of the spacecraft. And these 2 instruments are not returning routine measurements. They are returning surprises. In 2020, astronomers reported that both Voyager spacecraft had detected a significant and unexpected increase in the density of the interstellar medium as they travelled further from the Sun. The readings contradicted the simplest models, which predicted that density would remain roughly constant once a spacecraft cleared the heliosphere. Instead, the plasma was getting denser. The gradient appeared to be a large-scale feature of the local interstellar medium, stretching across a region far larger than the heliosphere itself. No Earth-based telescope could have detected this. Only a spacecraft physically embedded in the interstellar plasma, measuring particle densities in real time, could reveal that the space between the stars has structure and variation on scales that models had not anticipated. The plasma wave subsystem contributed its own discovery. By measuring the frequency of electron plasma oscillations in the interstellar medium, the instrument detected a persistent, faint hum. This was not a signal from a distant source. It was the baseline vibration of the interstellar plasma itself, the ambient electrical tone of the medium between the stars, never heard before by any instrument, because no instrument had ever been in a position to listen. The frequency of this hum corresponds directly to the local electron density, giving scientists a continuous readout of interstellar conditions along Voyager 2's path. These are the measurements that will disappear when the instruments are shut down. Not abstract data points, active discoveries, ongoing revelations about an environment that humanity has never directly sampled before and may not sample again for a very long time. Everything else will have been turned off, stripped away, sacrificed. With only 2 instruments operating, the power demand will be lower, which gives the thermal balance a small reprieve. Less power consumed means less heat inside the bus, but it also means less total demand on the RTGs. The remaining power can be directed more precisely toward the systems that matter most: the 2 instruments, the transmitter, the flight computer, and whatever heating remains active on the most critical propellant lines. At some point, likely within a few years of the cosmic ray shutdown, another instrument will need to go: the magnetometer or the plasma wave subsystem. The decision will be agonizing. Both instruments collect data that is entirely unique. No other spacecraft is in interstellar space. No ground-based telescope can replicate what these instruments measure. Whichever one is chosen for shutdown will represent the permanent loss of a type of observation that humanity may not be able to make again for decades or longer. After the second-to-last instrument goes dark, Voyager 2 will operate with a single scientific sensor. 1 instrument, 1 data stream, 1 remaining connection to the scientific purpose that has justified the mission's existence for nearly half a century. The spacecraft will have been reduced from a fully equipped planetary explorer to a single measuring device attached to a transmitter, a computer, and a set of thrusters that may or may not still function. Eventually, even that last instrument will be shut down. The power will no longer be sufficient to run it and maintain the minimum systems needed to keep the spacecraft alive. At that point, Voyager 2 will enter what might be called its post-science phase. It will still be transmitting, still sending a carrier signal back to Earth, still confirming that it exists and that its transmitter is functioning, but it will not be collecting scientific data. It will simply be talking, saying nothing except "I am here." That carrier signal phase may last for some additional time, perhaps months, perhaps a year or two, depending on how much power remains and how the thermal balance holds. The transmitter draws power. The computer draws power. The attitude control system draws power to keep the antenna pointed at Earth. Each of these systems generates heat inside the bus, and that heat keeps the propellant lines from freezing. But the total power available will be vanishingly small, and the margin between functioning and failure will be measured in fractions of a watt. At some point, the power will drop below the threshold needed to maintain this minimal configuration. The transmitter will fall silent. The computer will stop processing. The thrusters will go cold. The hydrazine in the propellant lines will freeze, not all at once but gradually, crystallizing in the narrowest tubes first, spreading as temperatures continue to fall. And then Voyager 2 will become something it has never been in its entire existence. Silent, unreachable, alone. But it will not stop. The spacecraft will continue moving through the interstellar medium at approximately 15.3 kilometers per second relative to the Sun. That is roughly 34,000 miles per hour. No force in interstellar space is strong enough to slow it appreciably. There is no friction. There is no air resistance. The interstellar medium is so thin that drag forces are negligible over any human timescale. Voyager 2 will coast on its current trajectory for an immensity of time that dwarfs the entire history of human civilization. In approximately 40,000 years, Voyager 2 will pass within roughly 1.7 light-years of Ross, 248, a small red dwarf star in the constellation Andromeda. It will not enter that star's planetary system, if one exists. It will not be captured by its gravity. It will drift past, a tiny artifact of metal and silicon and plutonium residue, moving through a stellar neighborhood that has no knowledge of Earth, no awareness of the machine passing through, no mechanism to detect it. In approximately 296,000 years, Voyager 2 will pass near Sirius, the brightest star in Earth's night sky. Again, it will not stop. It will not slow. It will simply pass through that region of space, as meaningless to Sirius as a grain of dust is to an ocean. On these timescales, the spacecraft itself will change. Not through mechanical wear, but through the slow accumulation of damage from cosmic rays and interstellar particles. High-energy protons and heavy nuclei, striking the spacecraft's structure over tens of thousands of years, will gradually alter the crystalline structure of its metals. Electronic components will degrade. The golden record, mounted on the spacecraft's side, will endure for a very long time because it is made of gold-plated copper, a material resistant to corrosion in vacuum. But even it will eventually be eroded by micrometeorite impacts over timescales of hundreds of millions of years. The spacecraft's orbit around the center of the Milky Way will carry it through different regions of the galaxy over hundreds of millions of years. It will pass through spiral arms and interarm voids. It will encounter regions of higher and lower interstellar medium density. It will be tugged by the gravity of passing stars, its trajectory altered by tiny increments over enormous timespans. Eventually, on a timescale of billions of years, the cumulative effect of these gravitational perturbations will make Voyager 2's trajectory essentially unpredictable. It could end up anywhere in the galaxy, but by then, the spacecraft will be unrecognizable. Cosmic erosion will have worn away surface details. The antenna will have been pitted and scarred. The golden record may be partially or entirely destroyed. The RTG boom, already depleted of usable fuel, will be a cold metal cylinder carrying the remnants of decayed plutonium. The bus structure, aluminum honeycomb wrapped in degraded insulation blankets, will persist as a shell, a geometric oddity drifting through a galaxy that has no context for what it is or where it came from. Voyager 2 will become a fossil. Not a fossil in the biological sense, but a fossil in the deepest archaeological sense. An artifact of a civilization, preserved not in rock but in vacuum, drifting through a medium so empty that the processes of decay are slowed to geological timescales. Now, step back from these projections and consider what the spacecraft's survival until this moment actually represents. Voyager 2 was designed for a 4-year mission. Its primary objectives were to fly past Jupiter and Saturn, collect data during those encounters, and transmit the results home. That was the contract. That was the engineering specification. 4 years, 2 planets, mission complete. Everything after Saturn was a bonus. Everything after Neptune was extraordinary. Everything after the heliopause was unprecedented. The spacecraft was not designed to survive in interstellar space. It was not designed to function on less than half its original power. It was not designed to operate with most of its heaters turned off, most of its instruments silent, and its thruster system running without backup. The fact that it is doing all of these things, right now, as you absorb these words, is the result of a collaboration between the machine and its makers that has lasted nearly 50 years and that continues with every command sent and every signal received. The machine contributed its margins. The thermal insulation was more effective than the minimum required. The electronics tolerated colder temperatures than their ratings specified. The RTG thermocouples degraded more slowly than worst-case predictions. The hydrazine did not freeze at the temperatures engineers feared it might. The spacecraft carried within its structure a resilience that its designers built in but could not guarantee. The makers contributed their ingenuity. They turned off heaters and watched the temperatures stabilize. They shut down instruments and redirected the saved power. They raided a voltage regulator's safety reserve for a few extra watts. They built a thermal model from scratch, nearly 4 decades after launch, because they needed to predict temperatures in propellant lines that the original designers never expected would matter this long. They devised the Big Bang reconfiguration, an operation that has never been attempted on any spacecraft, because the standard approach of sequential shutdowns was not enough. They patched flight software across 13 billion miles to modify thruster behavior and slow the clogging that threatened to end the mission in silence. Every one of these actions was a bet, a calculated risk. A decision made with incomplete information, transmitted across a 19-hour time delay, executed on hardware that cannot be inspected, tested on a spacecraft that cannot be retrieved. The engineers did not know if their solutions would work until they tried them, and trying them meant accepting that failure could be permanent. The Voyager mission has always been described in grand terms. Humanity's farthest reach, the first interstellar spacecraft, the golden record, the pale blue dot photograph. These are real achievements, and they deserve the reverence they receive. But the grandeur can obscure the smaller, harder truth beneath it. Voyager 2 has not survived because it was destined to. It has not survived because space was kind. It has survived because a group of engineers, many of whom were not yet born when the spacecraft launched, have spent their careers figuring out how to keep an old machine alive by taking it apart piece by piece. That is not a romantic story. It is a story about loss managed with precision, about accepting that survival sometimes means becoming less than what you were, about understanding that every system you turn off is a capability you will never use again, a measurement you will never make, a question you will never answer. The engineers have not saved Voyager 2 by adding to it. They have saved it by subtracting from it. They have kept it alive by deciding what parts of it can die. And they have done this knowing that the subtraction will eventually reach the core. There will come a year when there is nothing left to turn off, when the last instrument has been silenced, the last heater deactivated, the last watt of surplus power consumed, when the choice is no longer which system to sacrifice, but whether the spacecraft can continue existing at all. That year is coming. It may be in the early 2030s. It may be a few years later if the Big Bang succeeds. But it is coming, and no amount of engineering brilliance can stop it. When that day arrives, the silence from Voyager 2 will not mean the spacecraft has been destroyed. It will not mean it has frozen solid in the cinematic sense, encrusted with ice like a ship in the Arctic. There is no moisture in interstellar space to form ice. There is no atmosphere to carry frost. The spacecraft will simply be cold. Its electronics will be unpowered. Its propellant will be solid in the lines. Its antenna will point wherever it was pointing when the last thruster fired, drifting slowly out of alignment with Earth as the decades pass. The golden record will face outward into the void, its cover etched with diagrams explaining how to play it, written in a symbolic language designed to be understood by any intelligence that might find it. No one will find it, not for an unimaginably long time, if ever. The distances between stars are so vast that the probability of Voyager 2 encountering another civilization's sphere of influence is effectively zero on any timescale that matters to human beings. The spacecraft will drift through empty space, between stars, through regions of the galaxy where nothing happens for millions of years at a time. It will carry the Golden Record's collection of sounds and images from Earth, a message from a species that built a machine and sent it outward, and then spent half a century keeping it alive through stubbornness and sacrifice, into a silence so deep and so permanent that the message may never be received. But the message was never really for the aliens. The Golden Record was for us. Voyager 2 was for us. The entire mission, from the grand tour of the outer planets to the crossing of the heliopause to the decades of instrument shutdowns and thermal management, has always been a human story. It is a story about what a species can accomplish when it decides to build something, send it farther than anything has ever gone, and then refuse to let it die until the laws of physics make continuation impossible. Voyager 2 has not frozen in interstellar space because it was built with enough insulation to trap heat, powered by a radioactive fuel that decays predictably over decades, and managed by engineers who understood that every watt of power lost was a watt of heat that would never come back. The spacecraft does not survive because the universe is gentle. The universe is indifferent. The interstellar medium does not care whether Voyager 2's propellant lines freeze. The cosmic ray flux does not care whether the magnetometer is still recording data. The background radiation at 2.7 Kelvin does not care whether a machine built by primates on a rocky planet 13 billion miles away is still warm enough to send a signal home. The spacecraft survives because people care. Because engineers who inherited a mission from their predecessors have chosen, year after year, to study the thermal models, to analyze the power budgets, to debate which instrument to sacrifice next, to design creative solutions for problems that the original builders never imagined, and to send commands across a void so large that light itself needs 19 hours to cross it. They have done this not because anyone required them to, but because they understood that Voyager 2's voice, however faint, however diminished, however stripped of the capabilities it once carried, is still the only human-made voice speaking from interstellar space. And keeping that voice alive for one more year, one more month, one more day, matters. Voyager 2 will join the smallest and strangest category of human artifacts. Spacecraft on trajectories that will carry them beyond the solar system entirely. There are only 5: Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons. Of these, only the 2 Voyagers have confirmed crossings of the heliopause, the boundary where the sun's influence ends and interstellar space begins. When they stop, there will be nothing out there speaking for us. No active emissary, no functioning representative, just cold hardware drifting through the dark, carrying messages no one may ever read. The spacecraft will not know it has gone silent. It has no awareness, no consciousness, no capacity for loneliness or regret. It is a machine. Aluminum and silicon and copper and plutonium residue, assembled in a clean room in Pasadena in the 1970s, launched on a Titan Centaur rocket from Cape Canaveral on August 20th, 1977, and sent outward on a trajectory it will follow until the galaxy itself reshapes its path. But the people who built it know. The people who managed it know. The people who decided, year after year, which pieces of it had to die so the rest could survive a little longer, they know. And when the signal finally fades below the noise and the dishes turn away and the mission is formally ended, those people will know that they did not lose Voyager 2. They kept it. For decades longer than anyone had a right to expect. Through every trick, every sacrifice, every calculated risk, every sleepless night waiting for a response from 13 billion miles away, Voyager 2 has not frozen in interstellar space. Not because interstellar space is warm, not because the universe made an exception, not because the spacecraft was lucky. It has not frozen because it was engineered to retain heat, fueled by atoms that decay on a schedule measured in decades, wrapped in blankets that reflect thermal radiation back inward, and tended by human beings who spent nearly half a century deciding which parts of it had to die so the rest could keep speaking. That is not a miracle. That is something harder than a miracle. That is work. Patient, unglamorous, heartbreaking work. performed across billions of miles by people who will never touch the machine they are saving. And when the machine finally falls silent, it will not be because they failed. It will be because the plutonium gave everything it had. The thermocouples converted everything they could, the insulation held as long as physics allowed, and there was simply nothing left to sacrifice. The spacecraft will go quiet, the void will continue, and somewhere in interstellar space, still warm from the last heat its dying fuel could give, a machine built by human hands will drift onward into a silence that will last longer than our species may survive to remember it was ever there. Somewhere beyond the influence of the sun, a machine built by human hands is still warm enough to whisper, not because the universe allowed it, but because people on Earth refused to let it go silent one day sooner than necessary.